The last physical application that we are going to look at here in section 2.5 is that of hydrostatic pressure and hydrostatic force. Really, we're just focusing on hydrostatic force. The fact that we're going to be just assuming from physics here is that an object of surface area A in square meters at constant depth s meters below the surface of water is subject to force F equals rho, except rho here we know what it is, it's 9,800. 9,800 times A times S. So if you know the surface area of your object, you know the depth of your object, and that depth is constant, then what you can do is you can just multiply 9,800 by your area, by your depth, and you know how much force the water is applying to that object that you have. So for example 6, we're looking at a cylindrical tank. It has a circular base and it's oriented horizontally. The radius of the circle is going to be a meter and the length of the cylinder is 3 meters. If the tank is filled up with water, and in order to simplify this question, we're just going to assume that the tank is filled up with water. Not that it's filled up to the 1.5 meter mark. We will be able to do this question later in the course if it's filled up with water to the 1.5 meter mark, but as of now we don't have the integration techniques necessary to do this. So if the tank is filled with water, what is the force the water exerts on one of these circular faces? So the picture that we have here is we have some kind of circular face. We have horizontal cylinder here, and we know that the radius of the tank is 3. We know also, oh, nope, I lied. The radius of the tank is 1. The length of the tank is 3. So here's my picture. It's full with water, so we don't have to worry about drawing a water line. And we want to know what the force the water exerts on one of the circular faces is. So let's draw one of those circular faces in the plane that we're a little bit more familiar with. And maybe let's give it coordinate axes in the usual way. So, or at least in the nice way that the center of the circle is the origin of my axes here. So this is xy. And we know that since it's a circle of radius 1, the equation which describes it is x squared plus y squared equals 1. Cool. So the tricky thing that we're dealing with here is we can't apply this formula for force that water's applying because not every point on this end cap here, not every point on this circular face is at the same depth. Some points are feeling more pressure or more force than other points, and we need to find some way of accounting for that. So here what we need to do is we need to think about, well, which points are subject to constant depth? And the points which are at constant depth, which are the ones that we can deal with the force for, are the points on horizontal lines. So what I want to do here is I want to think about how much force is this horizontal line that I've drawn here subject to. And really I don't want to think about it as a horizontal line, but instead I want to think about it as a thin rectangle. In particular, the rectangle is going to have height dy. I need to think about this as dy because it is a horizontal rectangle and it has thin height. And the other quantity that I need to figure out about this is the width of it. Because once I know the width, I'll be able to compute the area of this thing. And once I know the area, that's one of the components that I need for the force here. So the area of the rectangle, well, we said it's going to be dy times the width. In order to think about the width here, we notice that the width is a varying quantity. So as I change y, if I move y down, it gets a little bit wider. If I increase y, it's going to get a little bit thinner. And so I need some formula to describe the width in terms of y. I'm thinking about the fact that I've got this dy here, so I want to integrate with respect to y. So I want to think about what is the width equal to in terms of y. Well, the width is going to be equal to the right or the coordinate, the x-coordinate on the right point minus the x-coordinate on the left point of this, on the left end of this rectangle that I've drawn here. So I want to think about this circle in kind of two different ways. I want to think about it in terms of the right half of the circle and the left half of the circle. So let's get a little bit different of a picture here, or at least start using maybe some different colors. So here's the right half of the circle in blue. Here's going to be the left half of the circle in green. And in order to get equations for each of these, and I want to solve for them x in terms of y, thinking about the blue represents the x-coordinates on the right half of the circle, the green represents x-coordinates on the left half of the circle. So I want to think about what is x in terms of y. So for the right half of the circle, or rather maybe we could just start with this equation here, trying to solve for x. So we'll have x squared equals 1 minus y squared. And then in order to think about the right half of the circle, or solving for x, I want to take square roots of both sides. So the right half of the circle corresponds to positive x values, so that's where we're taking the positive square root. And the left half of the circle corresponds to negative x values, so that's where we're taking the negative square root. So I have the right half of the circle and the left half of the circle written down here. And now what I can say is that the area of the rectangle is, well, okay, so we've already got the height, we need the width. So the width is going to be the coordinate on the blue curve minus the coordinate on the green curve. So let's write that down. So it's going to be the coordinate on the blue curve is 1 minus y squared, or root 1 minus y squared. The coordinate on the green curve is that negative 1 minus y squared. And simplifying a little bit here, I have dy times, well, if I'm taking root 1 minus y squared plus root 1 minus y squared, I get 2 root 1 minus y squareds. Cool, so I have the area of my rectangle here. I also need to know what is the depth of a given rectangle. Ooh, I misspelled rectangle earlier. Well, I know the y-coordinate, but the y-coordinate doesn't represent how deep below the surface of the water this particular rectangle is. For instance, the rectangle on the y-axis here is certainly not 0 meters deep, it's 1 meter deep. The rectangle maybe here at y equals 1/2 is going to be half a meter deep. At the very top it will be 0 meters deep, and at the very bottom it will be 2 meters deep. So the depth of the rectangle is the distance between the y-coordinate and y equals 1. In other words, the depth of a given rectangle is going to be 1 minus y. All right, so I have the area of a given rectangle. I have the depth of a given rectangle. That must mean that the force on a given rectangle is given by that 9800 number times the depth, 1 minus y, times the area, 2 times root 1 minus y squared dy. So now to get the force on the entire circular face here, I need to integrate this function in order to add up all of these forces. So let's see. So we need to integrate here, and we're thinking about, since we're thinking about integrating with respect to y, I want to integrate from the smallest y value where the water is to the largest y value where the water is. Well, the smallest y value is here at y equals minus 1, and the largest y value is here at y equals positive 1. So I'm integrating from minus 1 to 1 of twice 9800. We'll just leave it like that. Times 1 minus y, square root of 1 minus y squared dy. Great. So I have this formula written down, and I want to think about actually integrating. And you sit and you stare at this for a little while, and you notice that, well, this is kind of a tricky integral to be working with, as a matter of fact. It might be, since we've got this 1 minus y squared under the radical here, it might be nice to let u be 1 minus y squared. But in that case, du is going to have a y dy in it. And we don't have y dy, we have 1 minus y dy. So maybe what I want to do here is split up this integral into two different pieces. So I want to think about 2 times 9800. I want to distribute this root 1 minus y squared into the parentheses here, and then split up the integral afterwards. So I'm going to get the integral from minus 1 to 1 of root 1 minus y squared dy minus the integral from minus 1 to 1 of y root 1 minus y squared dy. So this integral right here is the one that we were just talking about we could solve by substitution. U equals 1 minus y squared is going to get us to integrate this thing here. But we still have the matter of this integral here, this first integral. And that one, we don't have the techniques yet to find an antiderivative of this function, but it turns out that we don't need to do an antiderivative in order to compute this integral because we can think about it geometrically. Thinking back to thinking back to our very first way that we sort of computed integrals, we thought about them as areas under curves. In this case, what we're actually computing here is maybe not the area under a curve, but this is the area of a semicircle, the semicircle 1 minus y squared, between minus 1 and 1. Area of semicircle of radius 1. So this first integral here, we can use our familiar pi r squared formula to compute its area, or I guess we're looking at pi r squared over 2 because we are looking at a semicircle here. And so this whole quantity here is going to be twice 9800 times the area of that semicircle. Well, it's going to be pi over 2 because we're looking at radius 1. In order to do this second integral, we said we could solve it with u equals 1 minus y squared, so that du is minus 2y dy, or du over minus 2 is y dy. So the integral itself becomes the integral from, let's see, so if y is minus 1, then u is going to work out to be 0. If y is plus 1, then u is going to work out to be 0. And the integral itself is, let's see, so du over minus 2 square root of u. But here we can stop because we notice that we have an integral from 0 to 0. So since the limits of integration are the same, this second quantity guaranteed to work out to be 0. Another way that we could think about this is what we have written down here is an odd function. If I plug in minus y instead of y, then I get minus y root 1 minus y squared, which is the negative of the function that we started with. Additionally, we're integrating over a symmetric interval. We're integrating from minus 1 to plus 1. So that tells me also that this integral should turn out to be 0. So however you want to think about it, whether you want to do the u substitution or notice that this is the integral of an odd function about a symmetric interval, it has to work out to be 0. So in the end, after all of this work, we get that this is twice 9800 times pi over 2 minus 0. The 2's cancel, and we are left with 9800 pi. Cool. So one observation that I want to make here with this problem is notice that this is 9800 times the surface area of this face here. So I don't know if that's coincidence or if that is bound to happen whenever you have a tank that's filled with water, but it's sort of a curious thing to observe here. The other thing to observe is that we never used this number 3 for the length of the tank. It just didn't play a role. It wasn't important. The tank could have been 100 miles long, it could have been an inch long, and the force that the water exerts on the end cap is still the same. So that's kind of another thing to keep in mind here and sort of observe as we're working through this problem. All right, I think that's it for section 2.5. I believe section 2.6 is going to have a couple more sort of physical interpretation sort of things, though maybe it will be less heavy on the actual I don't know, on the actual application sort of problems. We'll see.